Hello guys, today we are going to study about surface charge relation or surface charge distribution relation with the local radii of curvature in metallic bodies. So first, before moving on to the main topic, I would like to take it step by step. So the first step to understanding this concept is to take two metallic spheres and provide one of them with a charge q, right? And then just completely join them using a conductor. All right, so let's say the radius, my bad, let's say the radius of the first one is r1 and the radius of the second one is r2. All right, so what happens in this case is this charge will uh, move to this sphere until the potentials are same same potentials. So it will keep on moving until the potentials are same, because uh, we know that the charge moves from higher potential to lower potential, right? And the potential here is higher right now, so it keeps on moving and surfacing onto this one until the potentials are same. So the way we can study it is, we can call it q1f, which basically means the final q1, and we can call it q2f. All right, so now we can say that first of all we need to consider that they are very far away. All right, so they are not giving any potential on each other and or anything like that. So we just need to consider kq1f upon r1 for the potential of this sphere, and kq2f upon r2 for the potential of this sphere, right? And these both are equal, that is why the charges have stopped moving. All right, so what happens in this scenario is, uh, all right, just give me a second. All right, so what happens in this scenario is the movement of charges stops as soon as the potential is equated, right? Now we need to relate it with surface charge distribution. So we know the surface charge distribution is given by q upon area, right? So for q1, let's just remove the f for simplicity's sake. So the q1 can be given by surface charge distribution 1 multiplied by the area of the first sphere, which is 4 pi r1 cube. And similarly we can do this for the second charge, and it becomes r2 cube, right? uh, Sorry, r2 square, I'm really sorry. So we have the charges in terms of surface charge distributions, right? Now we can just put this inside here and put this side here. So because we needed to get the expression in terms of surface charge distribution, so what we get now is 1 by 4 pi epsilon naught 4 pi r1 square r1. So it becomes this, and this gets cancelled out, and then it is, and here is epsilon naught, this gets cancelled out, this is 1, this is 2, and r2 square upon r2. So yep, so what the expression that we get from all this is, it looks somewhat like this, right? Now we have studied proportionality in 8th class or 9th class, I guess. So by looking at it, you can imply, or you can say that this expression implies that the surface charge distribution is directly proportional to 1 by r, or inversely proportional to the radius. Now the above relation shows that for charged metal bodies, uh, at the same potential, the surface charge density is inversely proportional to the radius of curvature of the body. Now, in what other case have we seen that the potential inside a body or potential on two different points is the same? Try guessing it. Alright, so the answer to that is any conductor, any metal body. So this holds good for all metals, right? We can say that in all the metals, what happens is charge is distributed in such a way that as the radius of curvature, local radius of curvature gets smaller, the charge distributed there gets higher, the concentration of charges is higher, and it is lower in parts where the local radii of curvature is higher. So here it is very high, so it is very low. And if we were to try to visualize it, we can visualize it by the way that we can try to understand the repulsions, right? So in this area there is a lot of volume, right? There is a lot of volume. So if the charge is present here, there are a lot of atoms which will produce a repulsion. All right. So what ends up happening is this has the least amount of matter here. So the charge to provide stability to the system moves to the least populous area or the area with least matter. Even though this is not conceptually very accurate, you could try to visualize it this way. Now, the Van de Graaff generators also somehow work on this same theorem. That is why I actually wanted you to study this as well. Well, this is it for today. I'll be uploading some JEE Advanced PYQs for mathematics today as well. So stay tuned. Thank you.